We are honored to have him with us. I now invite Dr. S. Sivasubramani to deliver the inaugural address and continue with the first session.
Thank you for the introduction. Principal, other dignitaries sitting there, coordinator and the co-coordinator of this program. Very good evening to everyone and the participants. So as your principal said, the purpose of this online program is to disseminate the knowledge by experts during your free time. So you can join this workshop without attending this workshop physically. So otherwise, it would be difficult to go and attend. So that's why I could see more than 100 participants. So, and of course, it's difficult to join after your schedule, but moreover, it's somewhat convenient to join from your place wherever you are, so you can get some knowledge. So the purpose of conducting such workshops is to get some ideas, because we have to teach. When you teach, that teaching and research, we should always say that should go hand in hand. So when you do research and teach, it will be definitely better than when you teach alone. So suppose you may not be able to get the chance to do research also by participating in such kind of workshops, faculty development programs. You can get ideas of the latest, the state-of-the-art technologies of any field. As far as this workshop is concerned, the faculty development program is concerned, this title of the program is, I hope, it is Advancements in AI, IoT and AI for Smart Cities, Green Mobility and Sustainable Development Goal for Urban Transformation. It's a very good title. I think it covers almost the entire spectrum of engineering domain, starting from almost all domains. I hope the coordinator and co-coordinators should have invited speakers from various domains. So mostly the participants are also from different domains. So I hope the speakers, including me, will cover the overview of the entire thing, so that we will get a clear idea of what this workshop for the faculty development program is all about. And I would like to add one more point. I'm also going to organize one online FDP. That FDP is from September 22nd, 29. It's also a 6-day online program. I have already got 450 participants. So that is on a specific topic, AI, ML application in power systems. So I also welcome you participants to join that if you have time. So you'll get some ideas about, particularly on power systems, but this is a generic topic. So with this, I would like to thank the coordinator and the principal and other dignitaries for giving this opportunity to be part of this inaugural session and deliver the first session. I hope my session will be very fruitful and then it will be informative. So with this, I would like to thank you once again for giving the opportunity. Let's see with the introduction later after this inaugural session is over. Thank you.
Thank you, sir, for sharing your knowledge with us. Now we can continue.
It's okay.
Oh, fine. Okay. If you let me start my talk. If you look at the title of the talk, I have given a specific generic title. I hope the participants are from different domains. That means from different backgrounds, mostly maybe from engineering of different domains, electrical, mechanical, or maybe from from other domains also. So instead of talking about a specific problem, first I will give you an overview of this particular topic, and then I will touch upon some specific applications so that you will get an idea about what it is. And I'm a power system engineer. As this anchor person introduced me, I do research in power systems. And so it is, nowadays everybody talks about smart grids. It's also part of smart cities. So when you want to make cities smart, then you have to make each and every component of cities smart. So electrical grid is an integral component of anything. So first we have to make electrical grid smart. So before we see, let us first understand what it is and how we can make it smart. And then I will talk about AI and IoT application in smart grids. And mostly I will talk about the work which I have done with the help of my PhD students.
Before I talk about that particular work, I will just give you an overview of what it is, so that participants, even though they are from different backgrounds, will get an idea. So this is how my presentation will go on. The overview of my presentation is, first I will start with what an electrical grid is. Then I will talk about why we need to make it smart. And then when it comes to smart grids, and I will specifically talk about two important components. There are multiple components. I will talk about two important components from the electrical perspective. So there may be multiple things, but I will talk about these two things, mostly electric vehicles and then a microgrid. So these two things are an integral part of smart grid. I will talk about that, and then I will find at the end, I will touch upon the application of AI and IoT, in particularly in smart grid, so that you can make the grid smart and eventually you can make cities smart. That is how the presentation will go on. And many of you may be aware, if you are from electrical background, many of you may be aware what an electrical grid is. Electrical grid is nothing but it's an interconnect network. It's a group of, it's a group of wires. Mainly, you can say from a layman perspective, or from the power system engineer's perspective, it's an interconnect network having transmission lines, transformers, and various other devices. What is the purpose of that? The main purpose of the grid is to transmit electrical energy from source to the load centers. Load centers means consumers, like we are the consumers, so it has to be transmitted from the generating stations to the. That's a conventional way of defining this one. So this concept was conceived when electricity was invented almost 100 years ago. So we have been using the same concept. We generate electricity at some specific places in bulk way. Then we move that electricity or transmit electricity to the load centers with the help of this grid. That interconnect network is called electrical grid. And then later on, we found some advantages in connecting several such grids, mainly, to improve reliability and economy. So what we did is we interconnected several things to form a bigger grid. So larger grid we formed. And then later on, we went on connecting several larger grids to make the largest grid that we have done. The main purpose was to, the two major things that were behind this interconnection were reliability and economy. That was those were the things which were required long back. That's why we went ahead in interconnecting many things. Of course, everything, there are pluses and minuses. So the disadvantages, these are the advantages. Reliability and economy can be improved. There's no doubt. But there are some disadvantages. Suppose there is a fault in a particular system or in a grid that may affect other parts of the system. It's obvious. It's when there is a fault in one part, it may affect other parts of the system because everything has been interconnected. This is a disadvantage. But when it comes to advantages and disadvantages, advantages outweigh the disadvantages. That's why that particular concept we generate and then we transmit to the grid and then we distribute to the various load centers. This has been, we have been using it for long. Till today, we have been using this one. By and large, we have been using this system since beginning, since the invention of electricity. Now, but we are moving away from this concept. We have started moving. We have already started moving it. So that's why most researchers define the existing system as a traditional one, as a traditional grid. So what I explained orally, that you can see it in this picture. So if you look at this picture, there are big power plants which generate very bulk quantities, and then they feed power to the grid. The grid is just a big and a large interconnect network, and it transmits energy to consumers. There are 3 different types of consumers: residential, commercial, industrial users. Of course, they are all part of cities, of course, right? So, but if you look at this particular grid, nobody can say whether the power is coming from a particular source. It's not possible because the grid gets power from various sources, and its purpose is to move. And the system is such a large system. This has to be operated reliably, economically, right? That is the ultimate aim of the current power system engineers, the traditional grid system. Of course, okay, you may ask, okay, it has been going on, well, there was a problem. That even though it has some disadvantages, the probability of that particular disadvantage is very low. It happens, of course, it happens. When it happens very occasionally, but if it happens, the consequences will be very severe. But even then, we have been using the system. Right. Before I talk about the necessity of moving towards the smart grid or moving towards non-conventional system or non-traditional way of consuming energy, electrical energy, I would like to spend some time on some specific data so that you will get an insight about this one. We need to know about some specific data related to our country. If you look at the total installed capacity of our country, Assam, particularly June 13. So this data has been taken from Central Electricity Authority. It is available in the public domain. Anybody can look at it. Assam, this particular date, it's 485 gigawatt. But if you look at the contributions from various sources, we know that the sources can be classified into conventional and non-conventional, but mostly conventional, thermal, hydro, nuclear. That non-conventional, there are multiple ways, but renewable energy in that one is gaining more attention in the recent years. But if you look at this pie chart, you will get an idea. Thermal accounts for 50%. Renewable energy sources, mostly solar and wind, accounts for 38%. Nuclear, 2%, 9, that is in terms of numbers, 9 gigawatt. It has been there the same way since beginning, maybe for a longer period. Hydro, 10%, right? So if you look at the contribution of renewable energy sources, it was 13 or 12% a decade ago. Now it has come to 38%. Soon it will become 50%. Maybe it will cross 50% also, right? So that is how this growth has been phenomenal, particularly renewable energy source. But now the purpose of that one is to understand the installed capacity. But when it comes to electricity generation, that is installed capacity. But when it comes to electricity generation, particularly the day-to-day use of electricity, still the energy what we use in day-to-day lives, till today, even though we have done a significant growth in renewable energy installation, but we are getting mostly energy from thermal power plants. That's why this particular electricity, this is in terms of energy, that is in terms of megawatt installed capacity. If you look at this one, it's 68%. That means 2/3 of energy what we consume is still coming from thermal. And we know that electricity production using thermal power plant is not clean. It is affecting our environment, and we have to make our planet safe for future generation. Cities also safe for future generation. We should avoid this one. Then we should deviate from this one. And this is due to various other factors. Even though we have sufficient installed capacity, we may not in the renewable sector. It is not necessary that everything will generate because it has that intermittency issues. It depends on nature. So whenever there is sun, cloud, whenever there is sunlight or wind, then you will get. Otherwise, you are not able to get. And because of that, we are not able to completely get rid of this thermal, particularly thermal way of producing this. But we have to go further. Right. Now, if you talk about the emissions, of course, we all know most of the participants are from electrical engineering background. Some of them may be from different background. Electricity is one of the sectors which contributes, emissions. But there are other sectors as well. If you look at the manufacturing sectors, agriculture, transportation is another big sector. And then buildings, they also contribute something towards global warming. That is, they also produce greenhouse gases, not only electricity. But if you look at electricity and transportation, they account for almost 39%. manufacturing alone. Why I'm combining electricity and transportation? Because of nowadays the transportation is going towards green mobility. So when you talk about green mobility, then you have to have EVs. So EVs, mostly EVs, even you can have hydrogen fuel hydrogen based transportation also. So mostly electric vehicles, they use batteries. So batteries, they have to get electricity, they have to get charged from grid. So it is natural to combine these two sectors. If you combine these two sectors alone contribute for 40% of emission, almost 40%. So suppose we do something here, then we can reduce the commitments we made. So that's why these 3 slides have been given, just to get some insights about installed capacity from the Indian perspective and the electricity generation day-to-day lives. This is the emission sector-wise. So since I am from power system, I am a power system guy, then I need to talk about more on electricity and transportation. Transportation, mainly green transportation. Right. So now, and also if you look at the emissions by country, China accounts for 30%. And then you know that China and US, they are the largest producer of electricity, largest consumer of electricity. Of course, India is the 3rd largest consumer and 3rd largest producer of electricity. But even then, our contribution towards emission is less than 7%. But if you look at China and US, they're contributing more. 30, and China is the biggest contributor as far as emission is concerned. Next is US. All other countries, Japan, Russia, EU, European Union, if you will leave all those things, all other countries contribute 30%. This is just to give you an idea about contribution by different countries. Now, having understood the problems associated with electricity production and the transportation sector, emissions also. So we need to do something, otherwise the average temperature, global average temperatures may go up. So that is not good for our environment. So we need to do something to reduce this one. That's why all countries have committed. They sat together and then they agreed to reduce their emission by a certain percentage so that the global average temperature well below 2 degrees compared to the pre-industrial years. That was the agreement made in 2015. Of course, based on the agreement, many countries have committed to reducing their emission by doing something, particularly in all sectors. If you look at electricity, transportation, manufacturing, everything, wherever possible, they can do and they would like to reduce it. Every country has done. But particularly, they have to bring EVs also in transportation, and then particularly in electricity, renewable energy, as much as possible in that electricity sector. But as far as we are concerned, our country is concerned, what we have done is we have committed to increasing this renewable share to 40%. There's no doubt we already come to 33%. We will easily reach 40% by 2030. There is only 5 years left. We will be able to cross 40% also. There is not a problem. But the next thing is, in order to reduce emission from transportation sector, we need to do much about that. So here we have to reach a goal of 30%. That means if you look at vehicles on road, 30% of vehicles should be electric vehicles by 2030. Otherwise, we will not be able to achieve the targets decided by that agreement. And recently we have committed. Those things we committed in 2015, and recently we are committed to achieving net zero. Many countries have agreed to reach net zero by 2030, 2050, 2050, but India has committed to achieving net zero by 2070. Because we are a developing country, if you start working on many things, because electricity and everything, all sectors, whatever I have shown, they are directly related to our economy. So if you start doing, if you reduce something on that one, it will significantly affect our economic growth. So that's why our country has taken more years to achieve this target. So what we have achieved is India will achieve net zero by 2070. So that is our target. So to achieve the target, we have to go beyond 40% renewable and 30% EV, we have to go beyond that. We can do this one, right? So now, if you want to increase your renewable share, if you want to increase your electrical EVs on road beyond 30% or even 10%, 20%, 30% also, the existing grid may not be able to support. They may not be able to provide necessary support. So we need to modernize. There is no other way. Otherwise, you will not be able to meet those targets. Right? And the installed capacity, even though we have sufficient installed capacity, still in some places we are not able to meet the consumer's requirement. And we also know that since it's a developing country, the growth has been increasing exponentially. That is, demand, particularly demand, has been increasing exponentially. So in order to meet the demand and reach other commitments what we made, something we have to do with the existing system. And particularly, we have to get rid of as much as possible from polluted power plants. And also we should cut cost on the electricity. And we should, at the same time, we should try to improve our water quality, mainly power quality. And now India is pitching to produce chips. Even recently they have started a chip power plant. We are going to produce chips. Earlier, of course, every country is depending on Taiwan. Now, every country, after the Taiwan, China tension, and all countries have started producing chips themselves. That is semiconductor chips. So when you want to produce chips on your country, that factories, all factories should get electrical supply with the precise quality possible. Otherwise, chips you will not be able to produce high quality chips. Then nobody will buy that one. So your power quality, there's something with power quality, electrical energy, the power quality will play a major role in this one. So power quality has to be improved. And then we need to improve the renewable energy penetration. There's no doubt we have to improve. And the infrastructure, existing infrastructure, particularly transmission sector and distribution lines, they were, conceptual design almost 5 or 6 decades ago, but we are using it. We have been using it for the last 60 years. So they have already aged. And almost all the, infrastructure in the electrical system, are operating at their close to the maximum limits, at the limits. That means they are at the verge of the collapse. So these are the reasons why we need to modernize in order to achieve our target and then to meet our various other things. So there is no way we have to modernize the electrical grid. And then the one more thing is, in the current system, 25% of energy, whatever we generate, 25% is getting lost. Lost in the sense in terms of technical and commercial. So that's why I call aggregate technical and commercial. Technical it's nothing but I square R. That is I square R loss, normal, because of the conductor resistance. That we cannot do anything. We have done various things. Unless we replace the conductors with superconductors, we will not be able to reduce the technical loss. Of course, that is, we can minimize it by doing something. But commercial losses are there because of theft, because of metering malfunctioning and not reporting. So they are almost together at 25% in the current system. So why should we waste 25% of electrical energy and then in this thing? So we need to do something so that we can minimize it. So these are the reasons, these are the drivers behind modernizing the existing grid, or you can say the traditional grid. So this is how the concept was evolved. The modernization concept was evolved. First, we need to make the system somewhat smart. Earlier in the traditional system, most of the meters were electromechanical meters. There was no control over that one. And then what they did is they started replacing with some kind of automated meters or some kind of automated meters so that utilities or operators can have some control over certain functions. And later on, they started bringing some communication technology into the meters so that you can have bidirectional communication, so that you can access it. Not only you can access it, but you can also get information from that side, can receive from information. So advanced or automated metering infrastructure, then they started bringing this one. And later they started, having controls over multiple places with the help of recent communication and information technology. And you can literally say that with the help of IoT, and later on we will also add more things. This graph will extend. We can make it more smart. So by doing this one, we can somewhat, make the existing grid behave in a smarter manner or in a better manner. Finally, we will reach the goal of smart. And you have to understand, the more you do, it also requires more investments. It's nothing. There's no free lunch. You have to invest something, then only you can have a better system. So when you invest it, you will definitely expect some return on investments. So the return on investments that we have to see. The return on investments will be that whatever drawbacks I mentioned in that particular slide will go away. So we will get better system, better power, quality supply, and we will get many access, many choices. We'll get many things. So, and moreover, that it's a long-term process. We have to work towards in reaching that. Even in the sustainable development, urban transformation, this talk has been going on for long, but it won't happen immediately. We have to go component by component, one by one, and then finally we have to integrate all those things. Fine. At the end, eventually the system will be, smart with the help of various. It is applicable for all systems, not only in the electrical grid, in any sector. You can say you can go piece by piece. Finally, you make individual piece smart. Then all individual pieces, if you make smart, then you can make the entire system smart. Like that will go. So that was the evolution. Then what happened? They wanted to have a framework, particularly for the electrical grid. They wanted to have a framework, how we can achieve this one and what should be there in the framework. So they wanted to have some conceptual kind of model. So they started working towards that model. So what they did is, particularly this concept was started in the US, because of course it's a developed country, and moreover they are also contributing more towards emission, and they have to work towards to make something better. That's why the concept started in the US. So what they did is the US government back then, maybe a decade ago, asked their own standard department, that is NIST, is National Institute of Standards and Technology. The government asked them to come up with a conceptual model, how we can make the system smart, particularly electrical grid sector. So what they did is, even though there is no clear definition for smart grid. People say it's a modernized grid, it's an advanced grid, it's an intelligent grid, it's a grid with two-way flows of electricity information. Of course, all the definitions are equally applicable. So they came up with a simple conceptual model. They said that if you want to call a particular system, particularly electrical grid, smart, then it should have these things. It should be able to support a bidirectional source of energy, and it should use two-way communication and control capabilities. And then we can have multiple functionalities and applications toward this one. So they created some concepts on that one. What they did, the conventional system, a group of generators feeds power to the grid, and then finally consumers will get. But whereas here, even if you look at the electricity flow, it is bidirectional. It can flow from source to load, even from this side to that side also. That's why there is no arrow mark in specific direction. So it's clear. And in order to make it operate, you need to have some kinds of operators. There should be some service providers. There should be an operator, a system operator, and then there should be a market where everybody should be able to participate, because it's a competition-based system. Even customers can also generate power and feed to the grid after their consumption. Even generating company, it's not necessary that only generating companies will generate power and send. Anybody can generate and power. So in order to coordinate everything, we need various technologies, particularly the recent communication technologies. And this is also possible only with control over all the facilities. That how can we have control? With the help of IoT, we can control them, we can monitor them, we can do with it. So this kind of conceptual model we came up with. And then you should also keep in mind, this is a long-term process, as I said, and it requires a lot of investment. So it's not an overnight job. It will take sometimes decades, sometimes more than decades also to reach this kind of conceptual model. So even though there is no clear definition, there is no proper definition for that one. We loosely defined with various terms, but there are some benefits associated with this one. Some benefits are expected. They are inherent. Otherwise, why will we invest in this something, right? So these benefits, those grids should provide. Whatever the drawbacks were in the existing system, those things should be avoided. They should not be there in the system, in the new system. Then only we can say. Of course, reliability we have to improve. Quality should be more. Of security, system should be more secure because we are going to use various technologies, communication technologies. The data can be, hacked. By hacking the data, by injecting false data, even hackers can collapse the entire grid. That's possible. So we have to have improved kind of security. And facility, the existing facilities, whatever facilities in the current system, they are not utilized properly. They are utilized improperly. Improperly means not optimally, you should say. So this smart grid should support optimum utilization of existing facilities, so that we can avoid various other things that will lead to reduction in cost. That will save some money. That's how it should be. And it should be there should be improved resilience to disruption. In the current system, it's an interconnected system, it's a large interconnected system. If there is a fault, or if there is a fault, the faults can be very severe. If the faults are not identified and isolated immediately, the effects can be catastrophic. The entire grid can collapse. It's possible. So, but in the smart grid, if you make this grid smart, it should be able to improve resilience. That means even though there is a disruption in the system, that it should be able to come out of the disruption quickly. That resilience should be very high. And also, it should be able to predict its maintenance schedule. And if there is any problem with that particular thing, it should be able to self-heal. I will explain later how it can self-heal. That also we'll see. How is it possible? If you want to predict its maintenance, everything, then you need a predictive model. So predictive model, we can predict with the help of an AI model, AI technique. Machine learning AI techniques will play a major role in terms of predictive maintenance. And self-healing responses, we'll see how IoT and the system how that concept will play a major role in achieving this concept, self-healing responses. And it should be able to accommodate more renewable energy sources, that is distributed power sources. You may ask a question, you may think, it's also happening in the existing system. So what is the difference between that and this? How can we call that a smart grid? Of course, the current system is supporting. And as I said, we have already started moving towards smart grid. We have already started automating certain parts of the grid. So it has to be done for a longer period. Finally, we'll reach this one. Even then, in the current system, integrating large renewables is a problem. You may have heard, particularly people from the electrical background may have heard about renewable energy curtailments. renewable energy curtailment is, we know that renewable energy, they produce power when there is nature supports, when there is sunlight, when there is wind potential. Whenever they support, whenever they produce, the load may not be that much, the load may not be very high, because when the sun produces, when solar PV produces peak power at no time, the total load may not be very high. So it produces more. It has to be stored in batteries. We can use it later. Suppose you have other plants like base load power plants. Suppose they are operating. If you want to cut down the power production from base load power plants, it's a difficult job. What the current practice is, they will ask renewable energy sector to curtail the energy consumption. That means we are wasting its full potential. We are not, using its full potential because of the grid requirements. But that can be avoided by smart grids. We will see later how it can be avoided. That is what it has been mentioned here. It should be able to accommodate more sources. It should be able to accommodate more. And then it should be able to reduce the emission. That is the main purpose of moving towards this smart grid system. It should be able to reduce emissions by, supporting EVs and renewable energy power sources. It should be able to do that. At the end, but of course, we are the consumers. We should have, more choices in terms of electricity usage. And these are the benefits a smart grid should provide. Now, a simple table gives us a comparative analysis of two grids, that is conventional as well as smart. The communication in the conventional system is one way. Smart grid, it is two way. Even consumers can interact with utilities. Utilities can interact with consumers in the current system, only one way communication. Power flow, it's one way. Smart grid, two way. Of course, in the existing system also, in the current system, even you may have heard about net metering policy, where some consumers have rooftop solar PV on their roof, and they produce and then send power. Of course, it's happening. But in the smart grid system, it's going to have, it should be pervasive. It should be across everywhere. And generation in the conventional system, it was the concept. It was devised 100 years ago. It should be centralized in a bulk, in a common place. And now in the smart grid system, it should be distributed. It should be everywhere. Wherever you have potential, it should be able to generate and feed power to the grid. It should be distributed. And the conventional system, mostly it was conventional way, it was thermal, nuclear, hydro, and of course with small. But here in smart grid, it's expected that the generation sources of this category, they produce a very low emission, or they produce nil emission, zero emission. And then you know that the transmission distribution losses, I said, aggregate, the combined one was very high, 25% close to, but it should be less. It should be less in this one. Efficiency, there it was low, but here we can make it high. Of course, by reducing losses, we can obviously make efficiency high. Customer choices in the conventional system, very few, except in some places. Other places do not, consumers in other places do not have any choices. But in smart grid, consumers will have many choices. And then control, when it comes to control, here self-monitoring, huge control, self-healing. These are the major differences between the conventional grid and then smart grid. Now, after having defined the necessity of having smart grid and the benefits of smart grid, let me talk about the two important components of smart grid, as I mentioned in the overview slide. The two important components I'm going to talk about are, the one is electric vehicles, EVs. It is inevitable now. Everybody has started using it, purchasing and started using it. But with some caveats, the caveats in the sense, everybody has that problem, range anxiety. Whether EVs, can you make me go to longer distances? That anxiety is there. That anxiety is being shuttered out by providing more charging stations, fast charging stations, by which we can do that. That is a different way of research that is going on. But now I will focus mostly on the integration part. When EVs need electrical energy, of course, they have to connect to the grid. When they connect to the grid, if all EVs start connecting, charging randomly from the grid, the existing grid will collapse. Definitely it will collapse. If you look at, if you assume even with 30% of EVs, that is our target. That is our target by 2030. If 30% of vehicles, what we have, if they are of electric vehicles, if they start charging randomly, and then if they coincide with peak loads, peak hours, particularly peak hours, the particular night time is the most, there are two peaks in a demand curve. The nighttime peak is higher than the daytime peak. So if the all EV owners start charging their vehicles randomly, that will spoil the grid, that will impact the grid, and moreover, that will also affect other issues like power quality, stability issues, other issues also, because it has an inbuilt charging facility that has to come with power electronic based interface, and that will introduce a lot of other power quality issues and stability issues. That is why we need to, I am focusing on that particular part. That's why I have taken, this is one of the important components of smart grid, because they're going to get connected to the grid first. And then second component is microgrid. So smart is, we are going to make the entire grid smart, intelligent. That's true. Okay. How we have to achieve? It's not possible to achieve the entire system smart without making each and every component smart. So in that way, this particular component, the second component, as I mentioned here, that microgrid concept, as the name says, name is itself is self-explanatory. Micro means small, a small grid. This was defined by the Department of Energy, United States of America. What they did is, they have defined a group of interconnected loads and distributed energy sources with some clear vertical boundaries. That area will act as a single entity from the main grid. This area with some sources and loads should be able to work in two modes. It can connect to the main grid and work in grid connected mode. It can disconnect and work in islanded mode. So that's why I put the second important component in smart grid. This component and the main first component, electric vehicles, these two components will, by having these two components, we can achieve a lot of benefits, as I mentioned in the slide. We can achieve many things. So that's why I mentioned these two are very important components from the electrical perspective. There are several components in the smart grid, but I have focused only on two components, mainly from the power system, electrical engineering perspective. Other things are communication technology is also a big thing. Of course, you need communication expertise in that one to have, and then cyber security issues, other issues of that. There are several components. And smart infrastructure itself is another sector. But even though there are several things, I have focused on these two things, electric vehicles and microgrid. Now, I will explain later how microgrid and EVs will play a major role in achieving several benefits. Now, we know EVs, they use different energy sources for transportation. Of course, but majority of the EVs use battery storage, majority. But few of the EVs use other sources of energy. Sometimes they use fuel cell, hydrogen gas. Now people are using it, and then solar panel. They also have solar panel, and then electric generator. But most of the EVs, almost more than 2/3 or more than 80% EVs use battery storage as their primary source of energy. So these batteries need to be charged. So when they discharge, then those batteries have to be charged. So of course, these are the benefits. They are obvious, very cheap in terms of cost of electricity and cost of diesel or petrol or gas used in internal combustion engine. And then maintenance is very low, right? of course, the motto of going towards EV is environment friendly, and other benefits, health benefits, because of smoothness in driving, everything, you will get other health benefits in this. These are the benefits that everybody knows, they are obvious also. But now you can categorize them in two, there are mostly two types. One is battery, purely battery. Some types of EVs have two components. Hybrid form, they have internal combustion engines as well as battery based. They're called hybrid forms. But whatever be that one, they are going to get charged by connecting and plugging into the grid. So that's why they are called plug-in electric vehicles. Plug-in electric vehicles, that means they have to be plugged into the grid to get electrical energy to recharge their batteries. Whether it is a fully battery-based electric vehicles or plug-in hybrid vehicles, whatever it is, they have to plug in to charge their batteries. That's why they classified under this category. Now, as I said, I will give you an overview of this interaction issues. So that EVs have to be interacted with the electrical grid. So there are two types of interactions. So one type, for the first one is the normal one, that is charging mode of interaction. So in that case, the electrical energy will flow from grid to the battery. Because whenever the battery drains, we need to get it charged from the electrical grid. So that type of interaction is called grid to vehicle, G2V. The flow is from grid to vehicle. The second one is vehicle to grid. That means even some EVs with this facility can even supply or send their energy back to the grid. It's possible. So like the way battery can be operated, of course it's a battery. Battery can be operated as a source also. As a source, whenever the need arises. Similarly here, the electrical energy stored in the battery can be utilized, can be used, can be sent back to the grid when there is a need in the grid. So that during that time, the flow is the opposite. It is from the vehicle to grid. So this particular concept is called vehicle to grid. That is why if you look at this particular slide, here it has been shown that the arrows show both the directions towards grid to vehicle to grid. This V2G concept. So what is the need of having these two types of interaction is, what is the need of? First one is obvious. We have to connect to the grid to charge our battery. That's one, grid to vehicle. Okay, fine. That's okay. And the second one, vehicle to grid with discharging facility. That is this dual charging. What is that? With transferring power back from battery to that phase with the weather facility, we can achieve some benefits. What are the benefits mean? We can make EVs, behave like distributed energy storage. Like the source, we can use EVs. We know that most of the time EVs, if you use any vehicle, mostly it is used morning and evening. Remaining time it is parked in the parking lots or in garages, or maybe in some places it is parked. So what is the need of keeping it idle? We can extract that energy during that period so that we can use that energy to support some ancillary services in the grid. Ancillary services when there is a sudden peak, when during peak hours, we can utilize. Of course, we may think, what is the point of using one EV, whether it can support that much amount of energy required by this? Of course, these are all valid questions. But one vehicle cannot support everything, but you just imagine millions of vehicles, right? If they are there, if I can say 30% of vehicles, if they participate in this thing, there will be a huge, a significant addition towards this thing. That will be significant. So they can support some ancillary services. What it can do is, it can even swap the peaks peak period, and you can even value filling. What by charging and discharging based on our own schedules, we can change the pattern of the load curve also. What we can do is we can ask all the EVs to discharge during the value period. That means during the off-peak period, so that they can do, we can change the demand curve pattern. So they will, that with the help of vehicle to grid concept, EVs can bring in these benefits. And the last part is it can facilitate the integration of renewable energy sources. How? You know that the current system, the electrical energy, still 70% of energy is from this thing. If electrical energy stored in the battery, or if the EVs get electrical energy that is predominantly from thermal or other polluting forms of sources, then what is the point of adding more and more electric vehicles to the transportation sector? The transportation sector's emissions may go down. Currently it is 24% or 25%. It may go down to 10% or 15%. That's okay. But the remaining 15% will get transferred to the electrical sector unless that energy is produced from the renewable energy sources. So now what we can do is, with the help of this V2G concept, we can make that battery instead of normal batteries, we can use the EV's battery to support the integration of renewable energy sources. So these things will be possible when you have this vehicle to grid concept. So this is the second type of interactions. Of course, in order to achieve these things, there are some requirements. You cannot do it with one EV, as I said. You need a large fleet of EVs, very large fleet of EVs. At the same time, users should be interested in participating. Of course, when you participate in this thing, your batteries will have to undergo frequent charging and discharging cycle. So when they undergo frequent charging and discharging, its lifetime will get reduced. So of course, when you participate in this thing, definitely you are participating as a producer. So you will get some incentive. There's no doubt. Without cost, nobody will do. Even though there is cost involved, that means when you discharge electrical energy back to the grid, you are selling the power. Literally, you are doing that one. When you charge it, you are buying power. So by participating, selling, and buying, you can save some money. True. But at the same time, by doing in this activity, by participating in this process, you'll have to compromise on your battery's lifetime because of frequent charging and discharging cycle. So some may not be interested. So the user's interest is also very important, particularly in this concept. And in order to do all those things, you need to have a dedicated infrastructure. Otherwise, it is not possible. How can you do? It should be done from a parking lot with all those facilities. So the dedicated infrastructure is required. So these are the requirements. So, and this is the main component in electrical grid. This will have a significant impact in the smart grid system. A simple example can give you a rough idea. If you are skeptical about this particular concept, if you are skeptical, if you are not sure what is by one vehicle, how can you do this one? Just imagine 10% of 250 million cars, particularly we may not have, but developed countries, everybody uses car, it's possible. So just imagine 10% of 250 million cars, assume that they are of this category. And you know that currently the battery capacity is minimum 20 kilowatt hour, even beyond that also it is there, minimum, right? Even if you want to have a longer range, your battery capacity should be more. So if you assume that the battery capacity of 20 kilowatt hour, if you assume, then you look at the capacity, total capacity you will get from those 10% of vehicles alone, 500 gigawatt of electricity energy. 500 gigawatt hour is a huge amount. It's a huge amount. Charging is also a huge amount. Discharging is also a huge amount of energy, can be fed to the grid, can be taken out from the grid. So it's a simple example to understand, the benefits, or to give you an idea about this particular concept. So when they start interacting with the grid, and you can see the interaction can be fruitful or can be devastating, if it is not properly done. Right, now we have understood. So when they, even if they do not participate in the vehicle to grid concept, or even if they participate, it doesn't matter. But if there is no coordination among EVs, suppose there is no coordination, and they start doing it randomly, each EV starts charging, discharging, everything. If they do, even though there are multiple benefits, but when it comes to the electrical grid, it's also part of a smart city, a smart grid. This grid will have some impacts because of their interaction. The impacts are stability issues, power quality, line losses will also increase because finally they have to be connected to the distribution side. So when they're connected to the distribution side means definitely the current drawn by the batteries of all the vehicles through the feeders will get increased, and hence line losses will increase. This will also affect the main important thing of voltage regulation issue. Voltage at the far end of the distribution system, particularly in a radial system, will significantly go down. So this will affect the voltage regulation issue. These are the issues associated with this thing if there is no coordination among EVs. So what the researchers have proposed, a simple approach to overcome these drawbacks. There should be some coordination. That coordination can be made possible with the help of an operator, or with the help of a service provider, or with the help of a parking lot owner. A simple coordination. A parking lot owner can make a coordinated charging or discharging strategy. He can arrive at some schedule so that these problems can be solved. But here, if you look at this one, if you want to have this coordinated charging strategy, definitely there should be, he has to arrive at a strategy by taking care of several parameters: battery's capacity, of battery discharging capacity, as well as what is the battery state of charge when the vehicles come. So here, many researchers have started using AI, ML based techniques, particularly in developing this coordinated charging. Even my PhD students, two of my PhD students have been working on this particular topic. I will not talk about in detail in this thing, but I'm just giving you an idea where you can apply AI, ML application in this part. So this coordinated charging requires some kind of technique. You can utilize here AI, ML to arrive at a strategy by taking into various factors. Various factors means battery state of charge, state of health, and users' interest, users' driving behavior. So these are the future things. By taking care of all those things, by having a robust model, you can have a very good system in place, particularly in this thing, in order to work on this one. So this is possible with the help of AI. Nowadays, everybody is using. There are plenty of papers on this particular topic. This is one such component. The second component what I want to talk about is it's a microgrid. So though I explained, I gave a definition that has a clear definition, unlike smart grids. Microgrids are clearly defined. So this particular green part, this particular green area, why it has been shown green means because the entire grid is green. The sources are green. The consumption, of course, except this black one, there is a diesel generator just to provide some backup. All other things are green. There is a solar PV and then battery, the whole system is green. The emission is going to be reduced, everything. That's why it has been shown in green color. And this is a group of loads and sources with a clear electrical boundary, and that from the main grid's perspective will act as a single entity, and that entity can connect to the main grid with the help of the switch. The switch has been shown mainly to show that by flipping the switch, by making it on, we can connect this grid to the main. By making it off, we can disconnect it and work it in islanded mode. Possible, right? Why? When can it disconnect and work in the random mode? Suppose there is a problem in the main grid. Suppose there is a problem in the main grid. If it doesn't have this capacitor, this facility, then this particular area will not get electricity. Now it's a microgrid. It can disconnect itself. It can disconnect itself and work independently. Of course, it has sufficient amount of sources. It can work independently. So the power quality, reliability issue is satisfied. At the same time, it disconnected, it is working. The consumers in this locality, in this area, are getting power without any disturbance, right? And then once the problem is solved here, then this can connect to the main grid, and then it can interact with the main grid by participating in the buying and selling of energy. If it has surplus, it can give. If there is a shortage, it can take it from grid. That's how it works. And also, it can connect to the other parts. Just imagine if you have a system, if you have an electrical grid consisting of several such systems, several such microgrids. Assume like this. Assume a system having several microgrids, and then they disconnect and work independently. And when there is no issue, when they connect among themselves and work in a group in a grid connected mode. Just imagine if you have a system like this, then automatically that resilience, which was one of the, if you look at the slide, I mentioned that, which is one of the main factors in the smart grid, resilience, improved resilience to disruption. So by having microgrids, you can have an improved resilience. If there is a problem in main, it can disconnect and work. Once it is solved, it will connect. Similarly, you can have multiple systems, so automatically it will disconnect and connect, it will work. So this is how we can do. So now we can say a smart grid is a collection or combination of several such microgrids. So microgrid is, you can say, it's a miniaturized version of smart grid. If there are several microgrids, then the whole system will be called a smart grid. That's it. That's what I said. It is the second most important component from the electrical domain or operation perspective, microgrid. Of course, these are the advantages. Some advantages are obvious. Efficiency is very high, true, because you are generating at your doorstep or backyard or near your place, and then no transmission line. Of course, there will be improved efficiency. Reliability, of course, there is an improvement in reliability by disconnecting, and then you can still supply power to the consumers. And then overall energy consumption, you can minimize it by optimally utilizing the sources available there with the help of a market structure or with the help of predictive maintenance. And then, since it is expected that all the sources are of green and clean in nature, so definitely will have a reduced environmental impact. And then there is no congestion. Relief voltage the congestion in the existing transmission line is getting relief. The loss, because of there is no transmission line, the loss reduction is happening. And finally, the voltage control, because the sources are at the near the load points, so there is an improved voltage control. These are the technical benefits in terms of having technical and economical benefits in terms of having microgrids. Now, I will talk about one thing, particularly in the microgrid concept. One thing. This is where we can utilize this AI. As I said, AI ML is used mainly in the coordination strategy of EV scheduling. Similarly, in microgrid also, because we need to operate this microgrid in a grid connect in an islander mode independently. So for that, you need to have certain kind of an operating strategy or management strategy. So in order to understand that one, I am just explaining the concept with the help of this PV, wind, and load curves. Because in microgrids, predominantly the electrical energy is from solar PV and wind. But the green color one, the thick green one, is the load, is the PV curve, solar PV curve. Solar PV produces power, the peak power at noon, and then it stops producing after 8 p.m. or 8 in the evening. Then it starts producing only after 5 in the morning. These graphs have been normalized in the x-axis, y-axis. If you look at this thing, all the power, they are per unit. That means they have been normalized to the maximum value. But if you look at the, this wind, it is also in green color, but it is shown in the dotted lines. So dotted lines, if you look at the wind, it produces power at in the early morning hours, and then its production is very less about this one. Okay, fine. Now, if you look at the load curve, that is how our behavior comes, because everywhere, if you look at a load pattern of any city or any country or any locality or anywhere, because it's a combination of residential, industrial, commercial consumers, the load pattern by and large will behave like this one. So till 6 o'clock, 7 o'clock, the load will be minimum. Once we start doing anything, it will go to some peak in the morning. After that, there will be a peak in the evening. Of course, this curve is also normalized curve. We can have a 2 peak also with a duck curve. Also, people say, but it's a typical curve. I'm not saying this is the only curve, it's a typical curve. So there is a peak in the evening. But the problem with this one is solar and wind, when they produce, the load is less. When we need, they don't produce. So in order to overcome, a simple choice is storage. That is obvious. We need to have a storage mechanism in terms of batteries and something else. We can store the electrical energy whenever they produce, store them. Whenever they don't produce, we can use the storage we can do. This problem will arise when you operate microgrids in an islanded mode. That is in a non-grid connected mode. Okay, now that is the intermittency problem. That can be avoided by having storage. And if you look at the storage, we can have 3 types of storage. Battery, of course, simple, you can have. Compressed air, even you can store electrical energy in the form of compressed air. And later on, you can let the compressed air pass through the compressor, and then we can run turbine, you can produce electrical energy. That's possible. And also we can store electrical energy in the form of compressed air. And then the other category is pumped storage. You may have heard about this pumped storage. It has been there for long. Pumped storage. Even in few of the hydropower plants in India, they have this facility, pumped storage facility. These are the general ways. But when it comes to microgrids, the options are compressed air storage and battery storage, because you cannot have a big hydropower plant in a microgrid or in a locality where it is possible. But this slide is giving you the various forms of storage mechanism. Pump storage, you may know, when there is an off-peak period, you can pump the water back from lower reservoir to the upper reservoir and store it there. And during peak times, you can let the water flow through the turbine and generate electricity. That is how it works. It has been there for long. It's one of the ways by which we can do. But these are the ways of taking care of intermittency. These are the conventional ways. The battery storage, of course, we can do. But now, recently, we have started moving towards a different way of direction. This is the application of, or you can say in a new research direction. People have started using it. Maybe it was started a decade ago or something else, to take care of the mainly intermittency when you have a system with many, majority of sources are renewable and expensive. Apart from having this thing, because pumped storage hydro is very expensive, and also to construct that one, it's not easy. Compressed air storage, of course, you have to store, and leakage will be an issue. Battery, you can store, but battery is expensive, that also we know. So now, the recent thing is, we can do something in the load curve. That in the demand, we can do something. We can manage the demand side. So to take care of this intermittency problem. So that's why the researchers have started moving in the new direction, demand side management. I will focus on this particular thing in a few slides. I will talk about particularly its application of how it will play a major role in smart grids, eventually achieving smart cities, and then reaching the sustainable development. So what we have been doing till today is, what we do is we let the source of electrical energy, those electrical sources follow demand. so far it has been going on. Whenever there is an increase in demand, we will operate more sources. Whenever there is a reduction in demand, we will operate few sources. So at every instant, the demand and supply has to be matched. If there is a mismatch, if there is an imbalance in the supply and demand, then that will lead to stability issues that everybody knows. So that's why like every instant, whatever power we produce, that has to be consumed, plus the power produced has to take care of the losses. I'm talking about the real power. This balance has to be matched. Since the demand is highly unpredictable, of course, we can predict it. We do not know what the exact demand, even after 10 minutes also. It doesn't change. That is why what they do is they operate certain sources as base load plants throughout a day. Some sources as mainly to take care of peak loads during they operate during peak hours. Some plants in its conventional system, some plants like plants which can be started quickly, gas turbine, hydro, even hydro can also be started quickly. Those plants, they will operate as during peak hours. Our large thermal nuclear, they are mostly operated as like base load plants in a conventional system. But now we are moving towards smart grid, micro grid, everything. Where there's no flexibility of having those things. You are going to have with renewable energy sources, solar, wind, battery, everything. So solar and wind, they don't follow. They follow their own pattern. They follow based on the nature's nature. They follow nature. So what we can do is, instead of making supply follow demand, why should not we make demand follow supply? Why should not we adjust the demand pattern? Of course, it is not so easy, because when you want to change the demand, you have to change the load curve. When you want to change the load curve, you have to change the consumer's preference, their pattern, your lifestyle, everything has to be changed. So why should not we do? By doing this one, what we can do is, we can, you will see a significant change in this one. Of course, by making demand follow supply, we can reduce the storage size, we can minimize the storage requirements. So this particular concept, making demand follows supply, instead of supply following demand, that is called demand side management. Now it's that particular concept. It's because we are going to make the demand respond to the supply. That concept is called demand response. So this demand response, in order to achieve this one, it is highly impossible without having IoT, without having a dedicated or latest communication infrastructure. It's not possible, otherwise it's not possible. You need to have bidirectional communication between utilities and the consumers, because finally we have to change our pattern. And then sometimes we can make it automated also. We can make it automated. We can automate it with the help of several Internet of Things devices we can do. So this requires all those things. It's without that you cannot do it. I will explain in 2-3 slides instead of talking about this problem in detail. When my PhD students, myself and my PhD students have started working on this concept also, this demand response, where we can use AI, ML, as well as with the help of IoT, how we can make, even we can make in a small scale, we can make it in a big scale also, it's possible. So you can see it in this particular slide. Just imagine a house having a dishwasher, TV, refrigerator, everything. These are the devices we normally have. Let us first talk about the domestic consumer. Forget about industrial, and then this industrial consumer's pattern is not difficult. It's very important. It's highly difficult to change, because they have to run 24 hours, 24 by 7, 365 days. They have to operate their industries. You cannot. They are not flexible. Their loads are not flexible. because they have to operate. But when it comes to residential, particular residential consumers account for 25% or 30% in the total consumer market. So if we can change the demand pattern of residential consumers, we can achieve certain things. That's why my focus is on a residential consumer. Assume that a domestic consumer having these devices. So now let us assume that that particular house has a smart meter. That means that meter can interact with devices, all appliances, at the same time interact with utility with the help of bidirectional communication. Then only the meter can be called smart. Otherwise, the meter is a conventional electromechanical meter or digital meter, you can say, if there is no communication facility. If it can interact with both sides, then only you can call it smart meter. So, of course, nowadays, all the distribution companies, distribution boards across India have started procuring several energy meters, their smart meters. They can even track the data consumption sitting at their workplace, right? Later on, with the added more facilities, you can make these meters interact with utility also. So now, what it does is, if you look at this one, this meter is connected to all the devices. Communication flow is there. And then it is also interacting with an aggregator. This aggregator, what it does is, maybe for your house, maybe for a group of houses, you can say. That means the aggregator's job is to collect some data from various houses, and then he will play an intermediary role between individual consumers and the utility from where you are getting supply. So now, if you can adjust the consumption pattern of these things, appliances, as I said, there is a drawback in it. That means, since you are going to change your consumption pattern, that will affect your lifestyle. It may bring some inconvenience, there's no doubt. But at the cost of saving some money. Suppose by adjusting your consumption pattern by changing your consumption pattern from peak hours to off-peak hours, or from off-peak to mid-peak hours, by changing your pattern, by compromising on certain things, maybe your convenience, right? You can reduce your monthly electricity bill. This is an active, normal passive consumer. So nowadays, some consumers are active in the sense they can also produce electricity. They can even use the electricity for their own purpose. And later on, if they have sufficient surplus power, they can even sell it back to the grid. Those consumers called, in the recent literature, they are called prosumers. They not only consume, but also produce. That's why they're called prosumers. So now, with the help of the smart meters, that we can achieve certain things, right? So what it does is, it collects data from various appliances. How it can collect? That is possible only when the device is smart, with the help of an IoT, by having sensor placed in various rooms or something else, by collecting a data, and then even this meter can be programmed in such a way that at what time it should be operated, what time it should be disconnected, what time it should be changed. So by collecting information from this thing, by having a technique, you can say the technique can be developed with the help of an AI and ML. Why we need to use an AI ML here? Because here sometimes we need to predict certain things. We need to predict something. So that prediction we can use, we can achieve with the help of an AI model. So that this smart meters will be helpful in this one. So this will, what it does is, as I have explained in this particular slide, as far as the research topics are concerned in this thing, what we can do is, in this particularly the demand response concept, we can simply develop an AI technique. Suppose you assume that your house has a solar rooftop PV, and you have a small wind turbine, and you have certain demand. And by developing an AI technique, you can simply forecast the generation of rooftop, because you need to forecast it. You do not know what it will be. A simple AI model, a robust model, can predict it better than the conventional model. And then you, by with the help of the technique, you can, adjust you can create an algorithm or create a strategy, you can say, the strategy by taking care of all factors. What are the factors? My preferences. I know that some devices I would like to operate them without any disturbance. And then I should also know what the current electricity price, because the smart grid, the pricing system may be dynamic, may be flat, maybe three-part tariff structure. Three-part means certain period it may be very high, certain period may be low, certain period may be very low. So it's possible because during it depends on the peak hour and off peak hour. So I should know the price also. And if I know how much rooftop PV and wind, how much they're going to generate during that period, with the help of all those factors, by taking care of preferences, all those things, if I can develop an algorithm, right, that algorithm will come up with a strategy, and then that I can optimally operate all the appliances without, of course, by sacrificing certain things, without sacrificing fully, I can achieve, certain benefits. So if I can achieve certain benefits, if everybody does like this, the entire system, that microgrid, I can say, in the microgrid itself, whatever I said, the intermittency problem. Intermittency, I talked about intermittency, but in order to take care of the intermittency, so we need to have a storage mechanism. So instead of having a storage mechanism, we can encourage the consumers to change their load patterns so that the storage requirements can be minimized significantly. That is the idea. That idea is possible with the help of AI and ML and IoT. Without that, it is not possible. This interaction is required. Finally, we can monitor, control loads as well as renewable resources. Even, of course, you need to have battery, small battery energy system to take care of the requirement of battery energy system by operating in this manner. If you look at without any demand response, with the demand response, you can see a significant change in the battery requirement. Suppose you don't follow demand response, you do it randomly, then you may need some X amount of kilowatt hour battery. Suppose you do this way, and then you will see a significant reduction in the battery capacity that will give you a lot of savings in your investment in this thing. It's, if you look at, and also battery, even though it's good, but battery management system or battery after its lifetime is over, take care of that dead batteries itself is a big issue. So we can contribute in achieving sustainable development by participating in this. These are the ways by which you can do. So in order to achieve the main goal, making city smart, making sustainable development, so everything has to be done, the bits and pieces in that way, piece by piece we have to do. So then only we can, in every sector we have to do all this. This is one way where we can use this thing. AI can be used particularly in this concept. Now, when it comes to that IoT, this is the last slide, I think so. When it comes to that IoT, where we can use the IoT in particularly in this sector is, we need to have that interface. Then only we can interact. We can make these smart meters interact with all the devices. So we need to have some interfaces. There should be some sensors placed with which can interact, which can transfer the data from that to cloud or maybe to the meters wirelessly. That sensor should be able to transfer data, and then there should be interface with various other devices inside the simple home. That home can be called as a smart home, you can say, because if everything is smart, that home can be also called a smart home. And there should be some battery and renewable interface also. There also you need to have some interfacing mechanism that is possible with the help of sensor and load interface. These interfacing mechanism, with the help of interfacing mechanism, we can let this particular meter interact with all the devices inside the house. So in order to achieve that one, we need to have several modules, and these are the modules. And these modules have been listed in this particular slide. So by having these modules and with the help of AI and IoT, we can participate. We can make individual consumers participate in the overall sustainable development goal. So like that we can do. This is from the electrical perspective. This is from the electrical perspective. We can reduce various other things. So in order to prepare these slides, I refer to, these are the references, papers I initially used. So since it's not a, it's an overview of the research what we have been doing here, which I've shown very few references. Though we have done some research on this particular topic, got some research, published our findings in some research papers. Since the audience is from different backgrounds, if I talk about much about that, some audience, that is some of the audiences may not be able to get that, right? I will talk about in general. So these are the references I used for this particular topic. That's it. That's all about my presentation. Thank you for your time and thank you for listening to me all of this. If you have any questions or if you have anything to clarify, you can ask me or you can post it in the chat box. Or if somebody has posted it earlier, I can also see and answer if there are any questions.
Participants, now you can ask questions.
Sir, you in the last told that we can use AI for generating wind energy and as well as turbine.
No, not for generating wind energy. I said we can use AI model to forecast wind energy generation, just to forecast, not for generating. Generating, it depends on nature. So we can develop a better model to forecast what would be the power, but in a better manner, in a more accurate manner. That's why we can use AI there. That's what I said. Just for forecasting purpose.
Sir, can we use the AI for optimizing the generation or just for prediction only?
We can mostly use for prediction, but later on, suppose you want to change its like the way you said, like optimizing the power from wind and generation, solar PV. It's also possible. It's also possible. Suppose you have surplus amount from solar and wind, and you want to do, but mostly both of them are, they produce electrical energy with zero cost. So you have to utilize as much as possible. So this question doesn't arise optimization. Here, the thing is, only thing is you have to predict effectively so that you can operate the appliances. You can reduce the batteries storage requirements. That's what you can do. But in a different way, suppose you have solar, wind, and conventional way, where you can have an optimization problem, and then you can do it. But when it comes to this one, optimization may not be required. Here, it's mainly for prediction and developing a strategy to operate all the appliances in a better manner.
Oh, thank you very much, sir.
Okay. Somebody has raised a hand.
Hello.
Yeah, please.
Smart grid without connecting distributed generators.
Okay. Smart grid connecting without
Distributed generators.
No, then what is the purpose of see, if you start utilizing power from the main generators, then we cannot achieve all the benefits, right? We should try to generate power locally and then utilize it also, distributed power.
Sir, why I am asking is, there may not be natural sources for generation of renewable energy in some areas, some geographical areas. That's why I am asking.
In that situation, for example, suppose we do not have sufficient amount of course, you know that it is due to geographic location. So in that situation, you should try to have electrical energy. It's not only from renewable energy sources, maybe from other forms of renewable energy sources like biomass, other forms of energy sources. So with zero emission or less emission, even you can have diesel power plants also. That is also possible because you do not have. But the idea is to have a microgrid which should be able to connect and disconnect, work independently. If it is not possible, then you can have a system with only other sources also. But it is expected that it should be from low emission or zero emission sources. It should be expected. It is not necessary, it has to be compulsorily from that one.
Okay, thank you, sir.
Okay. One more participant has raised this her hand. Kalai Shelby, I guess. Kalai Shelby has raised her hand. If you can, I think if you have raised your hand for asking me a question, please ask.
Ma'am, are you there, ma'am? Kalachali, ma'am?
Sir, yes, sir.
Okay, I think you have raised your hand. Did you raise it by mistake
Sir,
or you
sorry,
raised
sir.
it?
By mistake, I
Oh, no
got raised.
problem, no problem.
Sir,
It's
how
okay.
are you, sir? I'm your student,
Okay.
sir.
My student.
Yes, sir. 2006 passed out BSNA.
Yes, I remember. Yes, from Medicine.
Sir, right now I'm in PSNA, sir.
Okay, good, great, good.
Okay, sir. Thank you so much. We'll talk later. Thank you, sir.
Okay, fine, we'll talk later. Okay, there is one more. There are many persons. I think I am familiar to many persons are there, I think.
Yes, sir.
Yes, yes, yes. Okay, if there are no questions, I think, and thank you all once again for listening to me all the way for 1 hour. Okay, I hope this session, was fruitful and informative. You may have got some ideas. Okay, thank you.